Hi everyone, welcome to Mostly Math. Today we will be evaluating the following trigonometric integral, which I have defined as IMN, since it depends on two integers, m and n, to be the integral as x goes from 0 to 2 pi of cosine mx times cosine nx, and we see that it actually is going to break up into three cases. The most important case is it's going to be 0 if m is not equal to n, pi if m is equal to n but they're both not equal to 0, or 2 pi if they're both equal and equal to 0. As for the usage of this integral, it comes up when you try to find the Fourier series of a function. You will usually have to multiply by cosine nx, and if the original function is also trigonometric, there could be a similar integral to this one involved. There are several other families which I'll discuss later, but they can all be derived using the same principles which we're going to discuss today, which will be the complex exponential representation of the cosine function. So cosine x is equal to 1/2 e to the ix plus e to the minus ix. This is going to be the main tool that we use in the evaluation of these integrals. So let's go ahead and get started with the most important case, which is the m not equal to n case. Oh, by the way, I don't know if these integrals have a name. I would call them the Fourier integrals. But this is already its own mathematical object. There's actually a continuous form of the Fourier series, which is known as the Fourier integrals. So I don't know what to call them. If you do, please leave a link in the comments. That'd be great. All right, let's get started. So if we consider I, m, and n for m not equal to n, using what I just erased, using this, we note that there are two cosines, so there's going to be two factors of 1/2, which is just going to immediately bring out to the front as 1/4. Integral 0 goes, x goes from 0 to 2 pi with respect to x, cosine mx, which is now e to the imx plus e to the minus imx times e to the inx plus e to the minus inx. And now, to proceed, instead of using a trig identity to convert the product of the cosines into a sum of cosines or sines, which can be done, we're instead just going to consider the exponential integrals. Multiplying this out, just 1/4, integral from 0 to 2 pi with respect to x of e to the im plus nx, second term, plus e to the im minus nx, middle term, plus e to the minus im minus nx, and the last term, plus e to the minus im plus nx. Some obvious symmetry to exploit here. We also notice that all the integrals are of the same form with a different constant, namely they're of the form of 0 to 2 pi with respect to x of e to the ikx, which for k not equal to 0, as they will not be since we have stated that m is not equal to m, this integral can be evaluated very easily by using the integral formula for the exponentials. This is just e to the ikx over ik, evaluated at x equals 2 pi and x equals 0. Just becomes 1 over ik times e to the 2 pi ik minus 1, which is 0 because we know in the complex plane that when we go around the circle, any multiple of 2 pi times, we get back to where we started, 1. So it's either 2 pi, 4 pi, 6 pi. Any even multiple of pi is always going to be 1. In fact, we can rewrite this as just minus 1 to the k power, which is of course 1 for any integer k. So we see that it is in fact 0. And just as an aside, let's also evaluate the case where k is equal to 0. Well, that's just the integral from 0 to 2 pi with respect to x of e to the I times 0, which is 1, which is 2 pi. So I just want to inform you of a useful notation to express this fact, which is useful in quantum mechanics and so forth. Using the Kronecker delta, we can write this as the integral from 0 to 2 pi with respect to x of e to the I kx is equal to 2 pi delta k0, where of course the Kronecker delta symbol, I'm out of room here. The Kronecker delta symbol is just defined as delta mn is equal to 1 if m is equal to n and 0 if m is not equal to n. There's actually a neater way to write this as well. If we let k be equal to m minus n, you can also write this as the integral from 0 to 2 pi with respect to x of e to the I m minus nx is equal to 2 pi delta mn. Looks much cleaner. I've seen this result used in complex analysis actually. In pure mathematics, you can use this as the representation of the Kronecker delta function. And in fact, as the name suggests, you can also use this as an analog for the continuous delta function. You can just immediately generalize this to in the following form. We would write delta of x minus y, or delta of x, if we go back to this notation here, is equal to the integral from 0 to 2 pi of, let's see, we have dk over 2 pi e to the I kx. This is how it's used in quantum mechanics, quantum field theory. You'll most frequently see this as a representation of the delta function. Actually, it doesn't matter if there's a plus or minus, you'll see them both. This does not affect the evaluation of the integral. I just wanted to indicate that this integral is closely related to both the Kronecker delta and the Dirac delta in the following senses. We only needed the k not equal to 0 result to proceed here. So the main takeaway from this mini derivation, excuse me, anytime we're integrating over a full period of e to the I kx for any value of k, it's always going to be equal to 0 if k is not equal to 0, which it is in all 4 of these cases. So without any further work, we can conclude that all 4 of these integrals are 0. And of course, this also allows us to conclude that the entire integral is equal to 0 as well. So thus the case is complete. The m not equal to n case is actually done. I assume that many of my viewers may have already known the results of the integral of e to the I kx. I just hadn't proved it on this channel. I thought this was a good opportunity to do so. All right, so let's look at the other cases. The other cases are actually easier. So if we wanted to consider now I of m equals n equals, no, I m equals n, this case here, not equal to 0. I'm going to consider I n n now. Well, this is just, so we had the cosine formula. We need cosine nx now, just 1/2 e to the I nx plus e to the minus I nx, of course. There's going to be 2 of these, so there's going to be a factor of 1/2. And this is actually going to be squared. So I'm going to square this now. Square all of this, we get 1/4 times e to the 2 I nx plus 2 times the cross terms, which cancel out, very important, plus e to the minus 2 I nx. And we're going to be integrating all of this. It just becomes 1/4 integral 0 to 2 pi with respect to x of e to the 2i n x plus 2 plus e to the minus 2i n x. And now we have a similar integral as before, so we know what to do. So the first and the last integrals we can see are immediately 0 because we have k being 2n. For this one, remember, we're integrating e to the ikx is equal to 0. That's our formula. K equals 2n, and of course k is equal to minus 2n in this formula. So both of these integrals are 0. We're left with the integral of 2, which we can definitely do. And our final result for the nn case becomes 1/4 times 2 times 2 pi, which is actually pi, exactly as I told you in the beginning. And now we just have the final easiest case remaining. I'm going to calculate I00 now. Well, that's pretty easy. It's just the integral 0 to 2 pi with respect to x of cosine 0 times cosine 0, which is 1, 2 pi. This proof's actually complete. Not really a proof, more of a derivation. And I just want to introduce the other integrals. You can certainly compute them for homework if you like. So there are other trigonometric integrals of the same form which are useful. So there's the integral 0 to 2 pi with respect to x of the same thing but cosine replaced by sine. And there's also another integral 0 to 2 pi with respect to x of one of them being cosine and one of them being sine. And there are similar values. You'll see a different value for this term because, you know, sine 0 is obviously 0. I believe the other values are the same, but you can easily look them up in a table of integrals if you have any uncertainty. And either way, you can also derive them very easily now that you are aware of the method how to do that. Just use e to the ix plus e to the minus ix for cosine, and the minus sign version for the sine, which of course, just for convenience, I'll write for you. Sine x is just 1 over 2i e to the ix minus e to the minus ix. These tools are all you need, along with, of course, the integral of 0 to 2 pi dx e to the ikx is equal to 0. That's all I need to prove these integrals here. They're very useful if you evaluate Fourier series. You'll see them all the time. And if you want to see more math, please subscribe to my channel. We'll see you next time.